All right, in this video we're going to be talking about Chapter 11, Ka and Kb. We're working toward that, and acid-base equilibrium is what it's really about. Now before we can get too far, we have to do our next little side topic, which is Bronsted-Lowry acids and bases. Okay, so in the last video we talked about Bronsted and Lowry redefined an acid as a proton donor and a base as a proton acceptor. Now, what you have to understand is what they were really talking about. Okay? So let's take an example. Let's take hydrogen for a second. Hydrogen on the periodic table is basically a 1 and a 1. That's one proton, 1 electron, no neutrons. Doesn't have any. So it's a really small atom. Okay? When a hydrogen becomes H+, what did it do? It threw away its electron. So when it throws its electron away, what is it really left? It's a proton. It's all it's left. So when they talk about proton donor and proton acceptor, they're talking about, H's. Okay? Things that are moving H's back and forth. And I'm going to show you a couple of examples. Okay? Proton donor is going to be giving away those things. Proton acceptors are going to be taking those in. Okay? So it's another way of defining a hydrogen ion. It's a proton donor and a proton acceptor. So let's take an example, and after I do a couple of these, it will be pretty easy to understand. When I have a hydrochloric acid, how do I know that's an acid? Because it has an H in the front. Reacts with water to produce H3O plus Cl minus. Okay, so let's define some things real quick. We know that's hydrochloric acid. This is water. This is weird right here. This is called a hydronium, sometimes called heavy water. And pretty much you can tell it's a water that has an extra H. Because if you have H2O and you add another H to it, what do you get? Well, you have H3O. Well, that's neutral. That's a +1. So all it is an H floating in the water that sticks to that, becomes a hydronium. Now, I'm going to go ahead and say this now, and we'll use it many times throughout this next unit. If you have an H+, that's an indicator that an acid was dropped in the water. Same thing here. Think sort of tomato. Sometimes they will write the formula and show you the H's. Other times they'll show you that high reactive ion right here will actually combine with water. Now, where'd the water come from? Because these are all going to be in solutions. So either one of these are going to tell you that an acid's been dropped in the water. It's called a hydronium. We'll see it many, many times. Okay. Now, what I want you to do is I want you to look at this equation, and I want to figure out what is happening to this guy when it goes from here to here. When this goes from here to here, what did it do? It lost its H. What is this guy doing? Because these are the reactants going to products, right? What is this guy doing? From here to here, it's gaining the H. So basically the H is being thrown from this guy to this guy. So if I'm correct, I wrote that wrong. This is the proton donor line, and this is the proton acceptor. Going from left to right, because as we go from left to right, we're going from reactants to products. So this is donating a proton. Okay? So what does that mean? This is and I'm going to abbreviate it like this, Bronsted-Lowry acid. Go back and look at the definition. It's a proton donor. This is going to be a Bronsted-Lowry base because it's accepting to go that way. All right? So from here to here, it's donating an H, so that's a Bronsted-Lowry acid. Well, it already is an acid by the normal naming. You'll see why in a minute. We have to have this definition. And then the water is gaining this. Now this confuses some people sometimes because we know water's neutral. Here's what's happening. Water is acting like a base in this reaction. It's acting like a base. It's taking on an H. Okay? Now, I want you to look here. The arrow is going both directions. So we were only talking this way. So let's talk about the reaction when it goes in reverse. Okay? So when it goes in reverse, not this direction, it's going to go this direction. Okay? What is this guy doing from here to here? from here, from the right to the left. It's gaining, okay? It's gaining, it's accepting a proton, right? So by definition, this is a base. What is this guy doing from here to here? He is throwing an H away. He's donating an H. So this is acting like an acid when I go this direction. Now, you'll notice I called this a Bronsted-Lowry acid and a Bronsted-Lowry base. That's correct. And this is acting like an acid and this is acting like a base. Now they decided when they were doing this, instead of calling them Bronsted-Lowry acid, Bronsted-Lowry base, Bronsted-Lowry acid, Bronsted-Lowry base, when somebody's talking about which Bronsted-Lowry acid are you talking about? Which Bronsted-Lowry base? So what they decided was on the right side only, they used the word conjugate, meaning in the reverse. So this is the conjugate acid, this is the conjugate base. Okay? So if you're going in reverse, this is like acting like an acid. So the word conjugate is never on this side. Never. Bronsted-Lowry acid, Bronsted-Lowry base. The word conjugate is only on the right side of the equation. Okay? Now, what happens if this reaction, they chose to write it the other way around? Oops. Because by convention, the reactants are always on the left, the products are always on the right. So if I go from here to here, what am I doing? I'm donating an H. So this is a Bronsted-Lowry acid. What is this guy doing from here to here? It's accepting it. So it is a Bronsted-Lowry base. Okay? Proton donor, proton acceptor. Now when I go in reverse, HCl is going to become Cl. It's donating the H, acid. So it's called conjugate on this side, conjugate acid. So this has to be the conjugate base. So you're going to use these four words. Now here's the one that really helps you. Whatever, so I'm going to draw this line from here to here. I want you to look at those two, and I want you to look at these two. And you probably already caught it. If something is a Bronsted-Lowry acid going in forward, what is it in reverse? It's a base. If it's donating going, then it's going to have to accept to come back. So if it's donating going forward, it's going to have to accept to come back. So your Bronsted-Lowry acid is going to be a conjugate base coming back. Whatever is your Bronsted-Lowry base is going to be your conjugate acid coming back. And that was true for this one as well. Whatever was an acid going this way was a base coming back. So if you're donating one way, in the reverse, it is the opposite. Okay? So let's try one that's not this reaction. Okay? Let's take this one. NH3 plus H2O produces NH4 ammonium plus OH minus. Pause the video and see if you can figure out Bronsted-Lowry acid, Bronsted-Lowry base, conjugate acid, conjugate base. Try it yourself and then come back. All right, let's see how you did. NH3 going this direction. NH3 is becoming NH4, so ammonia is becoming ammonium. What's it doing? It's getting an H, so this is a Bronsted-Lowry base. H2O is becoming OH on the other side, so it's donating it Bronsted-Lowry acid. I bet you got that. In the reverse direction, NH4 becomes NH3. It's donating an H, so that's the conjugate acid. So this must be the conjugate base. So let's check it out. Is it gaining an H to go from here to here? Yes, it is. So whatever was a base forward is an acid in reverse. Whatever is an acid forward is a base in reverse. Okay? Conjugate acid, conjugate base, Bronsted-Lowry acid, Bronsted-Lowry base. Now something jumps out real quick. It's this guy right here. Water was in both reactions we just talked about. In the first one it acted like a base, and this one it acted like an acid. There's a special word for this. called being amphoteric. Amphoteric. It can act like an acid or base, depending on what it's with. Okay? It can act like an acid or base depending on what it's with. All right, let me give you one more of these. I'm going to put this one out here, and then I'm going to let you figure it out. Here it is. Hydrochloric acid and ammonia produce ammonium. The reaction goes both ways, plus chlorine ions. Pause the video, you try acid base, conjugate acid, conjugate base. All right, so I want to point to this one real quick. We know this is a strong acid, okay? This is also, I'm going to tell you, is a strong base, okay? In one of the other videos, we will mention which are the strong acids and strong bases to make sure you have those memorized, but I'll just tell you, this is an acid in the base. But if you didn't know that, you could still figure it out. If HCl is becoming Cl, it's donating, so that's the Bronsted-Lowry acid. NH3 is becoming NH4, so that's a Bronsted-Lowry base. Why? It's gaining. It's a proton acceptor. Going in reverse, Cl becomes HCl. It's gaining an H. That's going to be the conjugate base. So this one must be the conjugate acid, which means it's donating. NH4 to NH3, it's donating. So I can see what's happening. Now, I want to add another term here. In the first two reactions, we had Bronsted-Lowry acid, Bronsted-Lowry base, but we had that water in there, right? In this case, we actually have an acid and a base. This is what we call a neutralization reaction. Neutralization reaction is when an acid plus a base yields a salt and water. Specifically, strong acid, strong base, they basically knock each other out. Okay, so think of it as Pac-Man and Miss Pac-Man. Okay, if you have equal amounts of each one, they knock each other out, and what you get is a type of salt. I'm not talking about NaCl every time. Okay, so this is an ammonium salt. Okay, and then you'd have water. Okay, now where's the water here? It's all poured into water. So you'll notice we're ignoring the water because the water's not part of the reaction like it was in the first two. I have this reacting with this. Now, that's poured into a water, so it's aqueous, so there's water there. This is poured into water, so it's aqueous. So when I pour it all together, it's water, 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 water. And so what we end up doing is just ignoring it all because the water is in everything. Okay? The water's in everything. Now, as we start walking through these things, I want to do something, and the first time I ever saw this, I thought this is really weird. I want to talk about pure water. Okay? Pure water, okay, at 25 degrees Celsius, basically room temperature, the density of water is 0.9971 grams per milliliter, because that's what density's in. Question I want to ask you is, what's its molarity? So I'm going to do this math. If I'm going to do molarity, it's going to be moles over liters, right? Well, I don't have moles and I don't have liters. But since it's water, I can figure it out. So watch this, 0.9971 grams per milliliter. I'm going to deal with the milliliters first. I know that 1,000 milliliters, why did I put it on top? So it'll disappear, is 1 liter. So now I have liters on the bottom. Grams needs to be moles. Grams to moles, by definition, 1 mole is so many grams. Well, water, on the periodic table, oxygen's 16, each hydrogen's 1, so that's 18. Okay? And so when I've marked everything out, grams, what do I have left? Moles per liter, which is molarity. So I'll put these numbers in my calculator. 0.9971 times 1,000 divided by 18. 55.4. The molarity of pure water is 55.4. That is an amazing number. The reason I say that is whenever we buy the strongest acids that we buy at the school that will eat through things very quickly, you're talking about 12 molar nitric acid that we sometimes get. We don't buy that one very much because it's so nasty, 18 molar, and yet water is 55.4 molar, okay? That is so weird, okay? But I'm gonna put this number up here for a minute, and then we're gonna come back to it. So I just will show you some things about water. And you know, you've heard things before like water is so unique, there's nothing else in the world like water, and that's exactly true, and all those kinds of things. But in pure water, from what we saw a while ago, water can actually do this. What was that thing called? Hydronium, that's right. Okay, if I balance it, that's 3, 4 hydrogens. Okay, so this is what pure water can do, okay? And we know that in pure water, there is 1 times 10 to the negative 7th molar of this, and 1 times 10 to the negative 7th molar of this. So in nature, looking at the numbers from what we just calculated, this 55 molar, 0.4 molar, and in pure water, you only have 1 times 10 to the 0.1, 2, 3, 4, 5, 6, that much. And 0.003456. Okay, those are small numbers. So what that really means is water is mostly this. There are those ions, but it's a small amount. It's like 2 parts per billion. Okay, 2 parts per billion. So there's not a whole lot there, okay, at all. So when we look at these numbers, and I just want to show you this real quick because this might be helpful to you. When you have this, if I'm correct from what we did in pH in the last one, this is how you calculate pH, and this is how you calculate pOH, right? The negative log of the H concentration or hydronium concentration. So what's the negative log of that number? 7. The pOH is the negative log of the OH concentration. When you put that in your calculator, what do you get? 7. Notice that plus sign? 7 plus 7, that's why the pH scale goes to 14. Because pure water is only those 2 things. 7 spots for H's, 7 spots for OH's, 14 total, okay? But in reality, that's just to show you how this plugs into one another. But in reality, there's not a whole lot of it that's in ion form. Most of it's still the H2O molecule. So if we do what we know how to do, okay, we're working toward acid-base equilibrium. Here's what we do, okay? Let's just call it Kc for right now. It's not really a Kc, but let's say K for water, okay? The equilibrium for water, if we do that, it's always products to their power, so 1 and 1, over reactants, right? Now we know how to do that. We've done that many times. Now remember, it's not a KSP, because in a KSP this is a solid, and so we ignore the water. So right now it's just like you did all the other things that we did, KP, KC. I'm just calling it KW just for water. Okay. Now if I want to get this fraction gone, if I put this over 1 and cross multiply, KW times H2O, I'm just doing some mathematical manipulation, equals that, right? Now, basically, if you have such small concentrations that we just talked about, okay, so in reality, there's water in everything. And basically the amount of water itself, if only small amounts are making that, this becomes negligible. Okay? It's basically in every one of the compounds. Every acid's going to have water, every base is going to have water, so we're pretty much going to ignore the water. So if we ignore the water that's in molecular form compared to ion form, what do you get? Kw equals this concentration times this concentration. Okay? And so, from what we just had, if I wanted to figure it out, 1 times 10 to the negative 7th, remember that number I just gave you up there? And this is 1 times 10 to the negative 7th. What's your K value for water? So 1 times 10 to the negative 7th times 1 times 10 to the negative 7th equals, oops, put that on the screen, 1 times 10 to the negative 14th. So your KW, your constant, equilibrium constant for water, is 1 times 10 to the negative 14th. Okay? And so what is really happening is this just verifies what we did with our pHs. So your KW is going to be really, really small. Why? Because most of it's still in molecular form. Just like what we sort of look like with KSP, there was so much that was in solid form. These powers are really, really big, so it's lots and lots of zeros at the front of the number. But this is the constant for water. Now, what that also tells us is a couple of facts. Okay? All right, be ready for this. Ready? Here it comes. If I dump an acid into water, this is pure water, when I dump an acid into it, let's say hydrochloric acid. In the hydrochloric acid, which particle, the hydrogen and the chlorine, is really the most important to acid base? The H. That's my spectator. And so what happens is, as soon as H, that's going to make this level go up, isn't it? Le Chatelier's principle says the reaction shifts the other way to solve that. Okay? So let's use a real example. Let's use a real example. We know how to do this math. Let's say that we're going to add 0.01 molar hydrochloric acid to this reaction. That's fine. Okay? So what's going to happen here? All right? Well, we know the KW, I'm going to switch colors so you can see it, is 1 times 10 to the negative 14th. We just had that, equals your H value is going to be a 0.01 common ion effect, molarity. What's your OH value? Okay, in pure water, this is 1 times 10 to the negative 7th, and this is 1 times 10 to the negative 7th. But watch what happens. When I take that 1 times 10 to the negative 14th, which I already happen to have on my calculator, divided by 0.01 equals 1 times 10 to the negative 12th. Okay? So my OH concentration equals 1 times 10 to the negative 12th. It should be in what? In pure water. Compare those two numbers. So Le Chatelier's principle holds true. When you dump in more acid, the reaction shifts to the left. So what happens? That level goes down, that level goes down, this level goes up. Right? Well, if that's going to happen, didn't the level go down? It exactly did. You're exactly right. It does that. Okay? And so what we're going to start learning when we start moving into Ka and Kb and acid-base equilibrium, we're going to start pouring different things into pure water, which are going to affect the pH, they're going to affect the concentrations, and they all work hand in hand with what we already know. All right? Now, last thing I want to talk about real quick is when we start talking about acids and bases, let me just talk about something like this to make sure we understand. Let's say I had a pH of 4 and a pH of 5, just to make sure people understand this. Which one's stronger? That one's greater because it's closer to 0. pH of 9, pH of 10. That one's greater. This is in the acid range, this is in the base range. Okay? Closer to 14. Okay? Now, here's what you need to know. When you are calculating the minus log of your concentration, you'll be doing that in this unit as well. So let's say you have your H concentration. Sure, we'll do it like this, which is going to give you your pH. Okay, if I plug in 1 times 10 to the negative 4th, the minus log of 10 to the negative 4th, that's equal to 4. That's how I get that one. If I plugged in 1 times 10 to the negative 5th, I get 5. That's how I get that one. But I want you to look at the difference between these two numbers that gave you a 4 and a 5. A lot of people think, oh, pH 4, pH 5, they're very close. They're really not. They're off by a multiple of 10. We'll write it like this. This guy is 10 times stronger than that guy. Why? It's a multiple of 10, which also means that this guy is 10 times stronger than that. Okay? So when you start looking at numbers, what does it mean to have a pH that's close? If you had a pH of 4.2 and a pH of 4.3, those are close. If you have a pH of 4 and a pH of 2, that's a multiple of 2, that's 100 times difference. Power of 2, power of 10 and power of 10, 10 squared. So from 2 to 3, 3 to 4, this guy right here is 100 times stronger than that one. So you got to keep that straight. Those concentrations can change very quickly, okay? And so when you look at those concentrations, you have to be able to manipulate it in your own mind. Oh, those are close. Those are not at all, okay? Last but not least, in one of the equations we had a while ago was a neutralization reaction. Here's what happens. This becomes very important. If your hydronium concentration equals your hydroxide concentration, you are neutral, okay? So basically all of these knock out all of these. So think of them as little soldiers. They're all lined up in the liquid, and all of these are lined up. And so these are going to knock each other out within the solution. If you have equal numbers, you're neutral. What do you think happens if you had more hydroniums than you do these? Then they're going to knock out some of them, but it's going to end up being a little acidic because I have H's left over. The same is true for bases. If you have more OHs than you do H's, they will knock out what they can, but what's left, the solution will be basic. Does that mean it's going to be a strong base? No, it just means it's going to be not exactly on 7. Okay? Now, the hardest part for us as scientists, or to do the science of it all, is that most acids and bases are clear. And so, how do we know these are happening? Well, we have to use what are called indicators. An indicator is a compound that changes color in the presence of an acid or base. Okay? Typically what's going to happen is when you're around an acid or a base, you're going to make a weak acid or a weak base and it changes color. Okay? If you've ever seen people check the chlorine and the acidity in a pool, they'll dip out some water, they'll put some drops in. When they put those drops in, they shake it up and it changes color, and they can look on the color range and say, okay, you're at neutral, or you're too acidic, so you're going to have to put potash into the pool. Okay, you don't want to get into a pool that's acidic, really acidic, because it can start to eat away at your skin, or too basic. Okay, and girls will know this. When you start using something like Nair or something like that, it's acidic and it's supposed to be on your skin for so long, and after that it starts to give you chemical burns. It literally starts to burn your skin. It eats the hair away, but after the hair is gone, it is starting to eat away at the skin. And so you want to get that balance back and forth between an acid and a base. The indicator helps you because it's a clear solution, so you can't see it. Okay? And so when you start talking about hydronium concentrations and OH concentrations, okay, if they're equal, you're neutral. If this one's too high, well, Le Chatelier's principle, if you dump more H in there, what's going to happen? Well, that's going to try to drop. And so they're opposites of each other. So why? Because pH plus POH equal 14. As one goes up, the other goes down. As one goes down, the other one goes up. Okay? Based on Le Chatelier's principle. Okay? And so in this video, we've learned multiple things. We've learned what the kW for water is, okay, and how that's used. We talked about pH, and we've walked through these different things. Now we're going to start using these skills to go a little deeper.